The redox-flow battery, shown here, operates in much the same way as the lithium-ion battery. In this diagram, I'm showing a full vanadium redox-flow battery. However, I don't intend to go into much detail as there are a multitude of different redox-flow battery technologies, all with their own different pros and cons, and it's unsure currently which technology will become prevalent in the future market. The redox-flow battery is often compared to the hydro pump. As with the hydro pump, if we need to increase the capacity, we just need a bigger lake. If we need more power, we can increase the amount of turbines. With the redox-flow battery, our electrolyte acts as the water. You can increase the amount of electrolyte to increase the capacity, and the battery stacks that connect the electrolytes can act like the turbines in the hydro pump. In this way, energy and power are separated in a redox-flow battery in the same way as a hydro pump. Also, like the hydro pump, the redox-flow battery has a relatively low energy density, so it requires a very large footprint. It has low standby losses, and since the electrolyte is far cheaper than the stack, the redox-flow battery is more economic for very large capacities and low powers, thus long discharge times. It's for these reasons of low standby losses and a favouring of long discharge times that the redox-flow battery is targeted at the 10 to 12 hour storage range, which is where lithium-ion batteries are too uneconomical to be used. Since when a redox-flow battery is charged, this charged electrolyte, as we see in the diagram referred to as the catholyte and anolyte, is stored in separate tanks. If we remove these charged tanks and created a vehicle to run off the charged power, we could use electrolyte in the same way that we use petrol now. And there is a concept car out there that uses this technology, although it has an extremely small range. Redox-flow batteries, in summary, are great for grid-scale applications and are almost cheaper than lithium-ion batteries when they have a very large electrolyte to stack ratio, even though they have a long way to go in their research progress. It is likely to be far cheaper than the lithium-ion battery and could revolutionise our grid-scale storage without the risk of huge battery fires that come with a lithium-ion battery, and with some technologies being used from easily accessible materials with no ethical concerns, as we see with cobalt and lithium.